Welcome to 2.1. This is Relations and Functions. Today you're going to learn how to analyze and graph relations and find functional values. First, let's start with some vocab. This is the Cartesian coordinate plane, typically known as the coordinate plane. It's composed of x and y axes that meet at the origin and divided into 4 quadrants. Our next vocab word is relation, which is just a set of ordered pairs. In the relations, we have domain and we have range. Domain is all the x values, range is all the y values. Next, we have function. This is where each element of the domain is paired with exactly one element of the range. Mapping shows how the domain is paired with the range. And one-to-one function. Each element of the range is paired with exactly one element of the domain. So here is our domain on the left and our range on the right. It's written in coordinate points. So you have -3 with 1, 0 with 2, 2 with 4. This is a one-to-one function because each range is paired exactly with only one domain. Okay. So here's our concept summary. This is our domain and range. It's a one-to-one function because, again, each range is paired with one domain. Our next one, -1, 5, 1, 3, 4, and 5, is a function. It's not one-to-one because notice that 2 of our domains is paired with one of our ranges. And then the next one, this is just a relation. It's not a function because -3 in our domain was used twice. So that one is just a relation, not a function. Alright, so example 1 here, domain and range. So it says state the domain and range of the relation shown in the graph. Is the relation a function? So our domain, this is our relation. R is -4, 3, -1, -2, 0, -4, 2, 3, 3, and -3. So our domain is all the x values. So it's -4, -1, 0, 2, and 3. Okay, then our range is -4, -3, -2, and 3. Each member of the domain is paired with exactly one member of the range, so this relation is a function. Definition. The vertical line test determines whether a function is a relation. So here the idea is we can draw a line straight up and down, move it from the left to the right, and it should never touch the graph more than once. If it does not touch the graph more than once, then it is a function. If it does touch, like on the right there, it intersects twice, that means this is not a function because the domain was used twice. So our example here, example 2, vertical line test. We have a table. We're going to graph this. It's 1950 to 2000. And we got our ranges. So when we graph, here are our points. And then to check to see if it's a function, we can use the vertical line test. And then we're just going to draw a line left to right. Notice that no vertical line can be drawn that contains more than one of the data points. Therefore, this relation is a function. Okay. Example 3, we're going to graph the relation represented by y equals 2x plus 1. So we're going to make a table of values to find the ordered pairs that satisfy the equation, choose the values for x, and find the corresponding values for y, and graph the ordered pair. So here's our x's. We're going to choose -1, 0, 1, and 2. Then we're going to substitute this into 2x plus 1. So we got -1, -1, 0, 1, 1, 3, and 2, 5. And we can graph it. And here's our line. Now we're going to find the domain range. Since x can be any real number, there's an infinite number of ordered pairs that can be graphed. All of them lie on the line shown. Notice that every real number is the x-coordinate of some point on the line. Also, every real number is the y-coordinate of some point on the line. So the domain and range for both are all real numbers. This graph passes the vertical line test. For each x value, there is exactly one y value, so that the equation y equals 2x plus 1 represents a function. So here's the vertical line test. Notice it only passes the graph once each time, so it is a function. Okay, example 4, what if the graph is a curve? So we're going to graph the relation represented by x equals y squared minus 2. We're going to make a table. In this case, it's easier to choose y values than the x values, and find the corresponding values for x. So these are the y values. We usually choose 0 and the numbers around it. So 0, negative 1, negative 2, 1, and 2. Then we're going to substitute this into x equals y squared minus 2. And we get 2, negative 2, negative 1, negative 1, negative 2, 0, negative 1, 1, 2, 2. Then we're going to graph it. So this is what our curve looks like. To find the domain and range, every real number is the y-coordinate of some point on the graph. So the range is all real numbers. So it's going to go completely up and completely down to positive infinity and negative infinity. But only real numbers greater than or equal to negative 2 are the x-coordinates. Notice that we don't go past negative 2 on the graph. So the domain is x is greater than or equal to negative 2. Okay. To determine whether it's a function, you can see from the table in the vertical line test. Okay, so there's the vertical line test, that there are 2 y values for each x value except for negative 2. Therefore, the equation y squared minus 2 equals x does not represent a function. Here's some more vocab. An independent variable usually is x, whose value makes up the domain. The dependent variable, usually y, whose values depend on x. Functional notation is just an equation that represents a function. So here's the equation, y equals 2x plus 1. If it's a function, we would write it as f of x equals 2x plus 1. What this means is it's the function of x, where x is the independent variable. Okay. So our example 5, given the function f of x equals x squared plus 2, and the other function g of x equals 0.5x squared minus 5x plus 3.5, we're going to find each value. So it wants a wants f of negative 3. So anywhere there's a negative, where there's an x in f of x, we're going to put negative 3. So we're going to start with the original function. We're going to substitute negative 3 for x, and then we're going to simplify. Square root of negative 3 squared is 9, plus 2 is 11. Okay, our next example, b, this time it wants g of 2.8. So if there's an x in the original equation, 0.5x squared minus 5x plus 3.5, we're going to substitute 2.8 for x. Then we're going to simplify. So we're going to do 2.8 squared times 0.5 minus 5 times 2.8. And then we're going to add 3.5. Sorry, and we get negative 6.58. Okay. This one we're going to do f of 3z. So wherever there's an x in f of x, we're going to put 3z. So we're going to substitute that in. We're going to square. 3 squared is 9. Z squared is z squared. So we got 9z squared plus 2. Okay. That's it for the lesson. Good luck on the practice.